This project shows you how to build a directional gyro or a heading indicator similar to what is found in general aviation aircraft. By the way, don't use this thing in a real plane. It's not that good. It uses a Bosch B&O 0859 degrees of freedom sensor, which is a MEMS chip. It's also got a TFT round display for showing you the heading and a Teensy 4.0 microcontroller to do the calculations and update the display. In the YouTube video comments section, you'll find the URL of the GitHub repository with the project documentation and other additional technical details, as well as a bill of material and a breadboard hookup diagram. So let's see how it operates. So this is what the directional gyro display looks like. And if you rotate it, you can see the compass rose is actually rotating it. By the way, this works in horizontal and vertical. There is a certain amount of tilt you don't want to go past. I think it's about 30 degrees or so, and you start seeing some directional errors. So remember, this is not magnetically driven. Compass rose is driven off the B&O 085 gyros and accelerometers. So it's not using the magnetometer portion of the chip. The whole idea with this project was to be able to sense direction through the gyros and rotating motion. The reason is to be able to ignore magnetic field and errors caused by fast turning, steel objects nearby, motors, that type of thing. So this is kind of what you would see in an airplane. Directional gyros in aircraft work off of a gyroscopic instrument inside, and it provides direction based on turning, not magnetic. So what you do when you first fire this up is you have to set the direction, right? So essentially what we're going to do is we're going to take a compass, magnetic compass, and we're going to use the A quad B encoder here to set the heading. This is really what you do in an aircraft. By the way, don't use this in a real airplane. This is meant for toys. So then what we do is we take a look at our compass, and we're going to set the gyro. We're going to rotate it west about, let's see, roughly 30, 40, 50, about 55 degrees or so west. So about there. Now, once we've done that, we don't need the compass anymore. We can take that away, and any turn now is going to be using those gyros. And the motion's very smooth. It updates at about 200 hertz in the B&O 085. The display only updates, though, if there's a motion of more than 0.5 degrees. So it's pretty sensitive. I mean, 0.5 degrees is pretty small. So we're not missing anything. And that also helps to keep noise out of it. So we have our Teensy 4.0 processor. We have the B&O 085 inertial measurement unit right here. Okay, a number of people sell those. The cheapest you can get is about $20. And then we have our A quad B encoder switch here, so that we can set the heading. Okay, initially at startup you do that, and as long as you don't kill the power, you should be good to go for that. The update rate for the display is about 200 times a second. So that's how fast it's going through the loop and checking. The max rate of rotations is 2,000 degrees per second. It's got 16-bit gyroscope in it, which is pretty impressive for pretty high resolution. But probably one of the key things with this the IMU down here, which is made by Bosch, it's running 32-bit ARM Cortex processor in that chip, and it's running software by Siva called Motion Engine. And that basically takes does all the work for you. It takes the raw 3-axis gyro and accelerometer data and converts it into something useful without you having to do a lot of calculations. And that's pretty handy, as opposed to the older 9DOF chips where you had to do computing yourself. So we actually use the gain rotation vector out of the chip. When you do your call, that's the information that you're getting and what you're going to be using to plot your display on. Okay. I think that's it for